Now we want to look at exponential functions, and I want to remind you to look in the lessons to review the properties of exponents. The thing about exponential functions is the exponent is where the variable lies, and there are two types. The first, we have f of x equal to a to the x. A is a number. A is greater than 0, but A does not equal 1. So an example would be f of x. Okay.
Since you went out of the frame a little bit.
Oh, shoot.
Freaked out.
I did. I'm going to go back to the frame in just a second. Okay. For example, we have a function f of x equals 3 to the x, or f of x equals 1.05 to the x. So as long as the base is a positive integer, positive number, and is not equal to 1, you have an exponential function. The second type, f of x is equal to e to the x, where e is approximately 2.71828 in a lot more unending, not repeating decimals. So it also has a base that is a number, but it is a very particular number, and this is called the natural exponential function, because that number appears everywhere in nature. Our variable x's in both of these can be any real number. So x is any real number. Positive, negative, fraction, 0, doesn't matter, which is why we need to review the properties of exponents. Let's think about what the graph of one of these exponential functions looks like. If x can be any real number, and x is our input, our domain values are all reals. Pick a point, say x equals 0, and if I'm looking at 3 to the x, if I have x equal to 0, 3 to the 0 is 1. So my f of x value or my y value would be 1. If x is 1, I have 3 to the first. X is 3. How about if x is negative 1? If x is negative 1, I have 3 to the negative 1. Now here's where the properties of exponents come in handy. Right offhand, I couldn't think of what 3 to the negative 1 is. But if you have a negative exponent, you can rewrite that value as 1 over 3 to the positive value, 3 to the first. So 3 to the negative 1 is the same as 1/3. So if I just decide to plot those 3 points, I have when x is 0, f of x is 1. If x is 1, f of x is 3. And if x is negative 1, f of x is 1/3. So my curve increases. I missed. Well, the easiest way to fix that is this way. There. So my curve is increasing forever as my values for x increase. The y values continue to increase. But as the values for x decrease, think about what happens if x is negative 2. If I have x equal to negative 2, 3 to the negative 2 is 1 over 3 squared, which is 1/9. So my numbers will get smaller, but they'll never reach 0. So my domain values are all reals, which you can also write as the interval from negative infinity to infinity, all real numbers. But the range values are positive numbers. F of x or y greater than 0. I never have y equal to 0 for my basic function. In a little bit, we'll look at a more complicated one that does move up and down. But this is the general shape of an exponential function. If I choose e to the x, well, e is 2.7, which is almost 3. So the shape will be very similar. And one thing to note, no matter what the base is, every time you plug in x equal to 0, you'll get y equal to 1. 3 to the 0 is 1. 1.05 to the 0 is 1. E to the 0 is 1. So for just a to the x or just e to the x, it goes through x equal to 1. X equal to 0, y equal to 1. But what about if my base is between 0 and 1? Here I did a is positive, but a is not 1, and I picked two numbers that are bigger than 1. Suppose we look at f of x equal to 1/3. To the x power. Let's plot some points again, and let's do the same three we did last time. -1, 0, and 1. So if I have 0, which is always the easiest one, this number to the 0 power is 1 again, so it does go through the same point. If x is 1, I have 1/3 to the first, which is 1/3. If x is -1, I have 1/3 to the -1 power. And there are a couple of ways to think about this, but one of them is now to think, I can take my negative, and instead of saying this whole 1/3 goes to the denominator, the negative will flip it. So this is the same as 3 to the first. So if I want to graph that with a different base, a fraction between 0 and 1, I still have the 1. Now, if x is -1, it's at 3. And if x is +1, it's at 1/3. But again, this function, 1/3, if x is 2, it'll be 1/3 squared is 1/9. It continues, but it still is above the x-axis. So again, the domain is all reals, but the range is positive values for y. This one decreases. This one increases. They don't go up and down. They just decrease and increase. And this is what just a general form of what an exponential function looks like. Let's look at a more complicated function. Now let's look at a more complicated function. F of x is equal to 3 to the -x plus 1. And to look at this, let's go ahead and plot some points and graph and actually look at the picture of it. I'm going to choose my three favorite x values first, -1, 0, and 1, leaving a little space in case I want to put some more in the middle. And the first one I'm going to check is 0. A -0 is still 0. 3 to the 0 is 1 plus 1. So this y value here is actually 2 when x is 0. If I put in x equal to 1, I have 3 to the negative 1 plus 1. Remember, 3 to the negative 1 is 1/3. 1/3 plus 1 is 1 1/3 or 4/3. If I put in negative 1, I have a negative of negative 1 makes it positive 1. So this is 3 plus 1, which is 4. So if I plot on a graph, at negative 1, I'm up at 4. At 0, I'm at 2. At 1, I'm at 4/3, a little bit above 1. So it is dropping like the one that was base 1/3. And let's go out and pick another value out here. What happens when x is 2? If x is 2, I have 3 to the negative 2 plus 1. 3 to the negative 2 is 1/9, 1 over 3 squared. 1/9 plus 1 is 1 1/9, or 10/9. Whatever, it's 1/9 plus 1 at 2. So it's a little bit closer to 1, but still above it. But notice the way it's going. This was 1/3 plus 1. This is 1/9 plus 1. The plus 1 part is going to stay common, but the 3 to the negative x part each time is going to get smaller. So we can think that this one actually will level off at 1. And so y equal to 1, we can think of as the lower bound. Like before, we had the x-axis as the lower bound. So it's the same general shape of the function, but this time it approaches y equal to 1 instead of y equal to 0. We want to compare exponential functions versus linear functions, because both of those functions can either increase or decrease. Linear can also be horizontal, but they don't have ups and downs. So it's very helpful if you have just data, just numbers and points, to try to determine how a function can be either linear or could it be exponential. We're going to assume first that our data is equally spaced inputs. So x would be 0, 1, 2, 3. The outputs are what make the difference as to whether it is an exponential or a linear function. So first, to look at linear. For a linear function, the outputs are such that the average rate of change which you know now is the slope, is nearly constant between consecutive values. So we're talking about our outputs, consecutive values, every pair, you do a rate of change, which is the slope, and the number should be nearly constant. We say that m is constant slope, but in real life data, sometimes when you round, they're constant, but if you don't round, they're not exactly constant. For exponential functions, ratios of consecutive outputs are nearly constant. So we're only talking about if our inputs are equally spaced for both. For a linear function, you do rates of change, you do the slope between your 2 points. For exponential function, you do the ratios of the consecutive outputs. And when it says ratios, that would be the fraction. Y sub 2 divided by Y sub 1 is about equal to Y sub 3 divided by Y sub 2, and so on. So we're going to look at some examples to look at function outputs in data and determine whether the function is actually linear or exponential. Let's look at some data involving 3 different functions and try to determine if a function is exponential or linear or maybe neither. The first thing to check is that the input data, the t-values, are equally spaced. Okay, so we do have that the t-values, where's my A? That's an A, that's a C. Whoa. There, are equally spaced. So 0, 1, 2, 3. It could also be 0, 2, 4, 6, but that's a different problem. So let's look at function f. Just look at the data first. 15, 20, it's going up. 13, it's going back down. 29, it's going up. So our data goes from 15 up, down, and then up. So that can't be a linear nor an exponential function because linear is increasing or decreasing or horizontal. Exponential is increasing or decreasing. So that this function, since the output values go up and down, it is neither linear nor exponential. Well, let's look at g. The way that we would test for a linear function first is to find the rate of change, or the slope. So we would need to do change in y over change in x. And my y values here would be 34 minus 37 would be a negative 3 change on top, and 1 minus 0 would be a change of 1. From 34 to 31 is another negative 3 change in output for a 1 unit change in input. And the same here, from 31 down to 28 is negative 3 for the output and then a positive 1 unit for the input. So there's a constant negative 3 rate of change. So our rate of change, which is slope, equals negative 3. So that means this is linear because it has a constant slope. This one decreases. So let's look at h. My numbers for h, if I just do my rates of change, I would do 24.6 minus 16.8, and 24.6 minus 16.8 is 7.8. It's an increase, again, over 1. But from 24 to 36, that's bigger. That's actually an increase of 11.5 units, but still a 1 unit increase in x. So far, my rates of change are definitely not the same. It's not a constant rate of change or even close to being constant. And from 36.1 to 53.1, that's 17 units change in y over a 1 unit change. So the rates of change here, these rates of change indicates not linear. So the next question is it exponential? So that we want to test to find out whether or not function h is exponential. Typically, for an exponential function, we have that the outputs have a common ratio. y2 divided by y1 would be about the same as y3 divided by y2, would be the same as y4 divided by y3, and so on. So let's check the ratios of the outputs. Let's go back up to the outputs for h. So we're talking h here. 24.6 divided by 16.8. So if I want to do that ratio, I get 1.4, and then we have to remember carry things out 4 to 6 decimals. So let's say it's 1.46428. So that's the ratio of y2 over y1, or in this case, y1 over y0. So our next ratio, 36.1 divided by 24.6. And it does have to go the next minus the previous. Okay? 36.1 divided by 24.6 is 1.46748. So these are a little bit different. They start off with the 1.46, and then the decimals after that are different. If I do one more, let's do the 53.1 over 36.1. If I do the ratio, I get 1.47091. So this 1.467 could round to 1.47. That's 1.47. 428, that's very close to being a half, so it's quite possible that this, depending on if these have been rounded to 1 decimal, if you continue to 3 decimals, we could say either 1.46 about or 1.47. They all round to 1.5 for 1 decimal. So I'd say for 2 decimals, we could say the rate of growth, let's say to 2 decimals, we'll call it 1.47, because these both round to 1.47, and that could be. Or if we were interested in just 1 decimal place, because our data is in 1 decimal place, we would round it to 1 decimal, which would make it 1.5. So that would be our base, that would be our A, our rate of growth in determining the function, and it is definitely exponential. Yes, it is an exponential function.